Okay, so the problem that we're doing here, it says an athlete throws a shot at an angle of 45 degrees at an initial speed of 43 feet per second. It leaves his hand at a height of 7 feet from the ground. Determine the maximum height of the shot and where the shot lands. So in order to solve this, notice both questions that are being asked are questions of position. What is the position of this this ball at these different times? Naming in particular height from the ground. That's the j component of our position vector. And when it says where the shot lands, that's horizontal distance away from the athlete. So that would be like the I component of a position vector at some specific time. How, though, do we determine this? So first thing we need to do is figure out how to use the function, or the position function that we have here. Okay, so v naught cosine of alpha t, that's my I component. H plus v naught sine of alpha t minus 1/2 gt squared. First thing I want to point out, g. We gave two approximations for g up here. We want to use this one, 32 feet per second squared, because everything here has been measured in feet. It has to be consistent. So let's start with that. What is our position function going to look like? R of t is equal to, again, v naught times cosine of alpha. V naught is our initial speed, which is 43. 43 cosine of 45 degrees. And that's our coefficient, t, and that becomes our I component, plus h, which is the initial height. It says that this is thrown from 7 feet above the ground. That would be a 7, plus v naught, which again is 43, sine of our angle, 45 degrees, and that's being multiplied by t, minus 1/2 times g, which again, remember we said was 32 in this case, t squared, and that will be our j component. Let's simplify that a bit. R of t is equal to 43, remember cosine of 45 is going to be root 2 over 2, so that's going to be 43 root 2 over 2 t, that's our I component, plus 7, this again is 43 root 2 over 2 t, and then 1/2 times 32, that'd be 16, so this becomes minus 16 t squared, and that is our j component. Now I should be able to answer both questions using this, okay? So what's the first thing that we're looking for? We want to determine the maximum height of the shot, where the maximum height of the shot and where the shot lands. So there's a couple of ways to do the maximum height. If we go back to our original diagram here, the maximum height is visually, I can see that it's right there. And if we know that this is a parabola, then that's the same thing as determining the vertex of that parabola, specifically the y coordinate of that vertex. So you can use algebraic techniques, because in algebra we learn techniques for finding the vertex of a parabola. But let's suppose that we just didn't know that this was a parabola. All we know is the calculus that we've learned. We're trying to maximize something, and we've learned how to maximize functions in Calculus 1. But it's important to note that we're specifically trying to maximize height. The height of this projectile is completely determined by the j component of this position function. So knowing that, I really don't care what's happening here. I want to focus only on this. I want to optimize this, so that means I'm looking for critical points, critical numbers. So if I focus just on that, and if I differentiate it, 7 plus 43 root 2 over 2 t minus 16 t squared, that would equal 43 root 2 over 2 minus 32t, and we set that equal to 0. Okay, so that implies that t is equal to 43 root 2 over 64. Just a couple of algebraic steps to solve that for t. Okay, well, I almost boxed that off. Okay, that's not my answer. What did we just find? What we found was the time at which the ball will be, or the shot will be at its maximum height. We didn't determine the actual maximum height. In order to do that, I would need to take that time, plug it back into my position function, and then determine what is the j component at that time. That would represent that maximum height. There's not really any purpose behind plugging it into the entire function because the I component's not important. So the maximum height then is going to be whatever I get from plugging this in for t right here. So that's going to be 7 plus 43 root 2 over 2 times t, which is 43 root 2 over 64, minus 16 times 43 root 2 over 64 squared. Okay, I would just go straight to a calculator there. What did I end up getting for this one? 21.45 approximately, and that would be measured to be consistent in feet, right? All right. Now, what's the next thing that we need? We need to determine where the shot lands. And how do we do that? Well, the key here is going to be thinking about what it means for our position function when the shot lands. When it lands, it's on the ground. And when it's on the ground, the height of that projectile would be 0. Or in other words, the the position function of our projectile is going to have a j component equal to 0. Okay, so let's work that out. If I were to take this j component and set it equal to 0, so 7 plus 43 root 2 over 2 t minus 16 t squared, set that equal to 0. You're not going to factor this, obviously, because of the root 2 in there, but you can solve this using the quadratic formula. Now, in my haste to get this done, I didn't actually write down what my solution to this was, so I'm just going to say t is equal to, let's call it t naught. Okay, that's going to be frustrating for some of you. So what I would say is use the quadratic formula, find a quantity, or find the solutions to this, and note also, kind of illustrate this. Remember, we're firing this projectile from a height of 7 feet, right? And it's a parabola. Notice that if I were to complete this parabola or draw some more of it over here, it's going to cross my t-axis somewhere over this direction as well, and that is going to be a negative t value. But t represents time since firing this projectile. It doesn't make sense to use the negative. So basically, this is just to show that the quadratic formula here is going to result in 2 solutions. One should be negative and the other should be positive. This one right here, I'm thinking of that as t naught. And again, you can find that value explicitly using the quadratic formula. I just forgot to write it down, and I don't have my calculator in front of me. So with that said, let's use that value, whatever it happens to be. What do we use it for? Well, again, we're trying to determine how far that projectile has traveled once it hits the ground. Or in other words, we can think of that as how far from the athlete the projectile ends up. And that would be horizontal position. That would be the I component of my position function. So what I would do is I would just plug t naught, whatever that turned out to be, use your calculator to find that, into my position function and get the corresponding solution. So that would be 43 root 2 over 2 times whatever t naught is. And again, we only care about the I component here. I already know that if I plug it in here, it's going to be 0. That's where we got it from. This one I do have the answer to. I just forgot to write down that one step. The distance, total distance traveled should be about 64.16 feet from the athlete. Okay? All right, cool. So at this point, I want to do what I had mentioned before, which is kind of explore a little bit the acceleration vector. And this is copied directly out of your book, which is why you're seeing, the little square blue 5, 6, and 7 and all that stuff. I didn't see much reason in just recreating all this myself, but I do want to talk you through it so that you understand where we're coming from. Okay, so remember, we've made some connections between velocity and our vector function r of t, which we now think of as representing position. And one thing we haven't talked about is that unit tangent vector. Let me back this up for a second. What is our ultimate goal here? Let me show you this picture. So if this is a space curve, this black curve right here, and we talked about how the acceleration vector should always point in to the curve somewhere, in towards the concavity of a curve. What I want to do is take our acceleration vector and decompose it into a tangential component and a normal component, which means I want to be able to write A as a scalar times the unit tangent vector at this point, plus a scalar times the unit normal at this point. Now, being a space curve, we would also normally consider the binormal vector. What if A, wouldn't A have to be a sum of scalar multiples of t and b? But what we're going to see here is that the vector A is always going to have, it's always going to be contained in the osculating plane where the binormal vector is always equal to 0. So this is the goal, so you're kind of understanding where we're working towards. And I just wanted to show you this picture. We're going to use A of t to represent the scalar that we'd be multiplying to our unit tangent vector. A of n is going to represent the scalar that we multiply our vector n by so that they sum to A. We call that the tangential component and the normal component of our acceleration vector. So with that, let's come back here. Notice, first of all, that if we looked at the unit tangent vector, the way that we defined it previously, it's r prime over the magnitude of r prime. Now, r prime, in the context of section 13.4, where we are right now, is our velocity function. So instead of writing r prime, let's write v of t. And the magnitude of r prime, which is the same thing as the magnitude of v, is what we think of as the speed of our particle. So this can be written as v over v, where this v is the vector function and this v is the scalar representing speed. If I were to multiply both sides of this by that scalar v, then I get that the velocity function is equal to the speed times the unit tangent vector. That really shouldn't be a huge surprise. Intuitively, we should have already known that because we know that velocity is tangent to the curve at the point that we're considering. And the magnitude of this v should equal lowercase unbolded v, which this would have that same magnitude. So that shouldn't be a huge surprise. But what I want to do with this relationship is use it to say something about acceleration. We know that the derivative of our velocity function is the acceleration function. So if I differentiate both sides of this with respect to the parameter t, notice I need to use the product rule. I have a product of a scalar function times a vector function. So that derivative will look like this: v prime t plus v t prime. Okay? Now, what we want to do is relate the acceleration vector and its tangential and normal components to the curvature concept that we talked about in the previous section. So leaving this here for a moment, remember that when we initially defined curvature, and then found an easier to work with formula for it. We showed that curvature is equal to the magnitude of t prime, the derivative of our unit tangent vector function, over the magnitude of r prime. That's the first of those useful formulas we came up with in 13.3 for curvature. The magnitude of r prime, however, is the same thing, as we said up above, as the speed of our particle at whatever time t we're talking about. So again, if I solve this for the magnitude of t prime, I get that the magnitude of t prime is equal to the curvature of the curve at that given point times the speed of the particle at that point. So curvature times speed. Okay? Now, again, we're going to leave that there. So I have something up here which I'm going to use in a minute, something right here which we'll use in just a second. But now we're going to start looking at our normal vector. Remember how we defined our normal vector. The normal vector was defined as t prime over the magnitude of t prime. And here, if I multiply by the magnitude of t prime, which is a vector, I get that t prime here is equal to the magnitude of t prime times my normal vector n. Here is where I can make a substitution for what we found up above. We found the magnitude of t prime to be equal to the curvature times the velocity, or sorry, the speed. So that says that t prime is equal to the curvature times the speed times the normal component. Now let's try to combine some of this stuff. So coming back up here, again, my acceleration, the goal was to break this thing down into a tangential component, or a sum of a tangential component and a normal component. And what we're going to do is make a substitution here for our normal component. Again, remember, t prime, which is showing up here, we just saw that it's equal to the curvature times the speed times the normal vector. So substituting this for t prime up here, notice there's another v already present there, which will multiply to this v, giving me v squared. So the whole thing reduces down to acceleration. My acceleration vector is equal to v prime times our tangent vector, unit tangent vector, plus the curvature times v squared times the normal vector. This v prime is what we're going to call our tangential component. I've already been using that term, which we denoted a of t. And that gives us this. A of t is equal to v prime. Our normal component, a of n, is equal to the curvature times v squared. Okay? I want to talk about an intuitive understanding of why these make sense in a physical context. So imagine for a moment that this space curve is actually a curve that you're taking in your car. So we're looking from like a bird's eye view. You're driving your car, and you're making a turn right here. The speed of the car at any given time, we know, should be given by v, right? But the curve is taking our velocity vector and kind of changing it. So when we look at our acceleration vector, we know that acceleration is the derivative of velocity. It kind of makes sense that the tangential component should be the derivative of the speed function. This part is a little bit more interesting in my opinion, because this is where curvature suddenly shows up. Remember that the tighter this curve, the larger the curvature is going to be. And what that means for us is that if we just hold v constant for a second, a larger curvature is going to correspond to a larger normal component. But if that normal component is large, it's going to pull our acceleration vector more this direction, more into the curve. And what does that mean? Well, if you've ever driven in a car and taken a really sharp curve, you kind of get thrown against the wall, and the reason for against the car door. And the reason for that is because there is a greater normal component to that acceleration vector, pulling the car around that curve more sharply, and you're because of your inertia, you're going to be thrown against the wall the other direction. Okay. In addition to that, if you take that curve at a faster speed, you're going to feel that force even more. So the normal component is influenced not only by the curvature at a point, but also by the speed at which you're moving around that curve. Okay, kind of an interesting way of looking at these concepts here. One other thing to notice, and I did mention this before, the acceleration vector was equal to a sum of scalar multiples of t and n, which puts it always in the osculating plane. Our acceleration vector will always lie in the osculating plane of a space curve at any given point. Okay, so now what we'd like to do next is derive some formulas for more easily computing our tangential and normal components that we just determined. So with that said, what if I were to take my velocity function and dot it with my acceleration function? Remember, the velocity function on the previous page we showed was equal to speed times the unit tangent vector. Acceleration we broke down into tangential and normal components, showing that it was equal to this sum right here. Using the properties of dot products, I can distribute this into the sum here and multiply the scalars together. I get v times v prime here, and then t dot t here. I get curvature times v squared times another v, so I get v cubed, and then t is dotted with n. However, remember, t and n are orthogonal to each other from how we defined them in the previous section, which means their dot product is 0. This whole thing goes to 0. What is t dotted with t? Well, remember, t dotted with t, just like any vector dotted with itself, gives you the square of the magnitude of that vector. But the magnitude of the unit tangent vector is 1. So t dot t is equal to 1 squared, or just 1. The whole thing reduces down to v prime, where these v's represent the speed. Okay? Now, again, remember, our tangential component for our acceleration vector is v prime. Here, if I solve this for v prime, by dividing both sides by v, I get v dot a, the vector function, is divided by v, the scalar representing speed, which is this. Now, putting everything in terms of our position functions, we have v dot a, which is the same thing as r prime dot r double prime. Remember, that's what v and a are, divided by the speed, which we know is the magnitude of r prime. So we get something that has some resemblance. It's not the same thing, but it kind of bears some resemblance to our curvature function. R prime dot r double prime all over the magnitude of r prime. Similarly, if I wanted to do something with the normal component of acceleration, curvature, we already came up with a formula for curvature in terms of r. And this is just from the previous section. R prime cross r double prime in magnitude divided by the magnitude of r prime cubed. That's curvature. But then we're multiplying that by v squared, the speed squared. Remember, speed is the magnitude of r prime. So the magnitude of r prime squared will cancel a little bit with this denominator, giving me this. Looks like the curvature formula again, but without this, the cube there. Okay, so let's see if we can work out an example here. We want to find the tangential and normal components of the acceleration vector of a particle with this position function. So we need r prime and r double prime. What is r prime of t? Well, that would be, I'm going to do this in component form, even though this is using standard basis vectors. That would be 1, 2e to the t, 2e to the 2t. Okay, and what about r double prime? That would equal 0 to e to the t, 4e to the 2t. Okay, now what do we need in order to come up with our tangential component? Well, according to this formula, I'm supposed to dot these two things and then divide by the magnitude of r prime. I'd better find the magnitude of r prime because I'm going to need that. What is the magnitude of r prime of t? That would be equal to the square root of 1 plus 4e to the 2t plus 4e to the 4t. This can be factored. This is equal to the square root of 1 plus 2e to the 2t squared. And then I can cancel the square root in that square. This is equal to 1 plus 2e to the 2t. 2t. So that simplifies things. Okay. Dot product. We need our dot product there. If I were to dot these two to find the tangential component for acceleration, that's going to be equal to r prime dotted with r double prime over the magnitude of r prime. That's the formula we just came up with. What is the dot product of these two vectors? Let me just use this. 1 times 0 is 0. 2e to the t times 2e to the t is 4e to the 2t. 2e to the 2t times 4e to the 2t would be 8e to the 4t, and that's all over the magnitude of r prime. That's 1 plus e to the 2t. Okay, this would be equal to, if I factored, for example, a 4e to the 2t out, e to the 2t times, that would be 1 plus e to the 2t over, or sorry, there should be a 2 there, missing my 2 there, 1 plus 2e to the 2t, which should equal 4e to the 2t for my tangential component. I'm seeing that I actually need to cut this video short. I'll finish this example up in the one last video.